physicists build a quantum lie detector, confirming true quantum behavior in large systems. In a landmark achievement, an international team of physicists has provided the strongest evidence yet that large quantum systems genuinely obey the laws of quantum mechanics, rather than merely imitating them. By performing Bell's test on a 73-qubit system, they have detected genuine quantum correlations that cannot be explained by classical physics. This breakthrough confirms that modern quantum computers are not only scaling up in size, but are also authentically quantum in nature, paving the way for more secure communications and more powerful quantum algorithms. If you like my content and want to listen more interesting science stories like this, then subscribe my channel, and don't forget to like and share this video with your friends and colleagues. Putting quantum systems to the ultimate test. For decades, physicists have relied on Bell's theorem, formulated by John Bell in the 1960s, as the definitive way to check whether a system truly exhibits quantum behavior. Bell's test can expose whether a machine is genuinely leveraging quantum effects, such as non-local correlations, where distant particles influence each other instantaneously, or merely simulating them through classical means. As quantum technologies mature and processors grow larger, these tests have become increasingly essential. In this new study, researchers took Bell's test to an unprecedented scale, examining quantum correlations in systems containing up to 73 qubits, the fundamental units of quantum computation. The collaboration brought together theoretical physicists Jordi Tura, Patrick Amonts, and PhD candidate Meng Yao Hu from Leiden University, alongside colleagues from Tsinghua University in Beijing and experimental physicists at Zhejiang University in Hangzhou. Quantum non-locality at scale. Quantum mechanics describes the strange and counterintuitive behavior of the smallest particles in nature. One of its most astonishing predictions is quantum non-locality, the idea that entangled particles can affect one another instantaneously, regardless of the distance between them. Though once controversial, non-locality is now well established and was recognized with the 2022 Nobel Prize in Physics. This research focuses on demonstrating these Bell correlations in large, complex systems, which is far more challenging than testing a few particles in isolation. A clever experimental strategy. Instead of trying to directly measure the extremely complicated Bell correlations in a many-qubit system, the team took an ingenious approach. They focused on energy minimization, a process that quantum processors already handle efficiently. Using a superconducting quantum processor, researchers engineered a special low-energy quantum state across 73 qubits. They then compared its energy to what would be possible in a purely classical system. The difference was extraordinary, 48 standard deviations below the classical limit, making it virtually impossible that the result was due to statistical noise. The team then went a step further by verifying genuine multipartite Bell correlations, a more demanding form of non-locality, in which all qubits in the system must be entangled and contribute to the quantum correlations. They successfully demonstrated this across up to 24 qubits, creating and validating a series of specially prepared low-energy quantum states. Why this breakthrough matters. This experiment provides the first large-scale certification of deep quantum behavior in a system of this size and complexity. It demonstrates that quantum computers are not just growing in qubit count, but are also improving in their ability to display, sustain, and prove fundamentally quantum effects. These findings have direct implications for the future of quantum technology. Understanding and controlling Bell correlations in large systems can lead to more secure quantum communication through device-independent cryptographic protocols, stronger, more reliable quantum algorithms, and better methods for verifying quantum processors as they scale to hundreds or thousands of qubits. Conclusion. By building what is essentially a quantum lie detector, physicists have shown that today's large quantum devices are not merely elaborate classical machines. They truly operate within the strange, non-local realm of quantum mechanics.